Intelligent Transportation Systems Podcast. Welcome to the ITSPodcast. Welcome to episode 29, October 2015. This is a special episode of the ITSPodcast about a just finished 18th IEEE International Conference on Intelligent Transportation Systems that was held in the Canary Islands from September 15 to 18. We have put together some nice contents for our unique audience. We have included nothing less than one of the keynotes delivered at the event. In particular, we have Professor Hermann Winner from Darmstadt Technical University in Germany. His keynote was really interesting. If you want to see it, please check out the YouTube channel of the conference. This podcast post at ITSP.cei.com. The title of his talk was How to Address the Approval Trap for Autonomous Vehicles, a survey of the challenge on safety validation and releasing the autonomous vehicle. We have also some comments from Professor Matthew Barth, President of the IEEE Intelligent Transportation Systems Society, and Miguel Angel Sotelo, Program Chair of the event. We hope you enjoyed this episode. Let's start with these two statements from Barth and Sotelo. Hello, we are now with Professor Matthew Barth from University of California at Riverside, President of the IEEE Intelligent Transportation Systems Society, Mother Society of the ITSC 2015 conference. Hello, Professor Barth. Can you please comment on this recent event?
I sure would like to. So very good to hear from you, Javier. So we had a very good time at the ITSC 2015. It was in a very unique venue. We had a great time and a beautiful place to have a conference. The conference itself was fantastic in the sense that it had a lot of people. I think it was our largest conference yet so far in our society. We had excellent parallel sessions. We had excellent keynote speakers. And I was surprised that every session had very good attendance, and the quality of all the papers seemed to be very, very high. So I was very, very happy with the conference.
Professor Barth, this will possibly be your latest participation in the ITSPodcast as ITSS President. You will hand the presidency to Professor Daniel Zheng with the start of the new year. What are your impressions on how the society has moved during your term?
Well, it's been a very interesting, very good 2 years as president of the ITS Society. So I went into this, knowing a little bit, but certainly at the end, I know a lot more about how the society works, how IEEE works. And so it was a pleasant surprise. I remember when I started my term, the previous president handed it off and told me some things, but of course, much of it you learn as you go along. So I think the society as a whole has improved. We continue to have improvements year by year. So I'm very happy and very proud that, we've expanded our membership. We've added some additional elements to our society. We have a new vice president of education. We have a new transactions that we've launched. So I'm very happy the way things turned out. I also learned a lot again about IEEE and how it works, and it's a big, complicated machine. And so, as long as you learn all the different parts, I think it's a great society. I think it's a great organization, and I'm very happy to be part of that. I'm positive that our incoming president, Daniel Zheng, is going to do a fantastic job. He's been involved with the ITS Society for a number of years, and I think he's going to continue to do quite well in that position.
Well, excellent. Thank you for your comments.
Thank you. Goodbye.
We are now with Professor Miguel Angel Sotelo from University of Alcalá in Spain. He has served as Program Chair of the 18th IEEE International Conference on Intelligent Transportation Systems. Hello, Professor. Congratulations. Can you please comment on the technical content of this conference?
Hello, Javier. How are you? Yeah, sure. First of all, I would like to say that I am proud to be the Program Chair of ITSC 2015, a conference that has set a new record of participation in ITSS-sponsored conferences. In particular, we have received 872 submissions from 46 different countries. Then, after the review phase, 475 papers were accepted yielding an acceptance rate of about 54%, something that speaks very much in favor of the technical quality of the conference. In the end, a total of 1,457 authors from 42 different countries have contributed to the conference technical program. The main contributors are three traditional countries. One is Germany with 91 accepted papers, then China with 71, and then the US with 66, followed by other countries in Europe and Asia, such as Italy, Netherlands, France, Sweden, Spain, Japan, and Singapore, just to mention the top 10. More than 600 delegates have registered and enjoyed the technical program of the conference, which have been broken down in 59 regular sessions, 11 special sessions, 14 workshops, and 6 industry tracks. And this is quite a relevant figure, because the industry track has included 30 oral presentations. This indicates a clear growing trend in the involvement of industry in ITSC conferences, something that I am sure will boost cooperation between industry and academia in the field of intelligent transportation systems in the coming years. All in all, I think we can say that ITSC 2015 in Las Palmas has been another great gathering of the ITS Society. If I may add something, in my view, the ITS Society is not only growing in terms of number of members, which is something quantitative, and it's excellent, of course, but it is also growing, more importantly, from the qualitative point of view. What I mean is that I see lots of familiar faces in all ITSC conferences, but also an increasing number of young researchers joining the wave, socializing and interacting with senior researchers and colleagues from industry, and contributing to building links and networks among the conference participants. And all of them enjoying a fantastic atmosphere, by the way. This is no doubt resulting in an attracting force that is making the ITS Society a bigger and more influential organization in the field of intelligent transportation systems worldwide, being our conferences a crucial, a very important tool for such purpose. As a conclusion, as program chair of ITSC 2015, I'm really proud to be part of it.
Well, thank you, Professor, and congratulations again.
Thank you, Javier.
Goodbye.
Bye.
Okay, are you ready to listen the Hermann Winner's keynote? Again, it is titled How to Address the Approval Trap for Autonomous Vehicles, a survey of the challenge on safety validation and releasing the autonomous vehicle. And it was delivered on September 17 during the third day's opening session of the ITSC 2015 conference. The keynote introduction was made by Professor Christoph Stiller from Karlsruhe Technical University in Germany. Enjoy.
This gives me the opportunity to introduce our next keynote speaker. Next keynote speaker will be Hermann Winner, and we are proud in our society to connect industry and academia. And Hermann Winner himself is one very good example because he did that in one person. After he received his PhD in physics, he joined Robert Bosch in Germany in 1987, and there he started in the Prometheus program, which, as you might know, has been the European highway automation and intelligent vehicles program. After that, he became responsible for bringing ACC and by-wire systems into the market, and he did that successfully around the turn of the century, I believe. So he can rightfully be recognized as one of the pioneers of ACC from an industrial perspective. And today, since 2002, he's full professor at the Technical University of Darmstadt, of course, looking at automotive technology. And 2012, he has been awarded with the Institutional Lead Award for this. And his talk will be about the approval trap and how to avoid it. I'm very interested to see what you have to say to that.
Thank you, Christoph, for the nice introduction. Good morning, ladies and gentlemen. I will give a talk how to address. I'm not sure that we can avoid, but we will see at the end of this presentation. What is an approval trap? Let me introduce something. Just a mental experiment. You just think some years or decades far from now that the development of an autonomous driving vehicle has finished. And then you will say, okay, let's go to the market. And of course, there's a prerequisite to say the risk of autonomous driving should not exceed the risk of conventional driving. I think it's normal common sense to do this. But then we come into some trouble. We have to get a kind of approval that this requirement is fulfilled. So we can develop, perhaps we can also produce on the risk of the manufacturer, but for the usage we have to have an approval. And for this, a validation process for that risk estimation. Let's have a look into statistics. German statistics, doesn't matter, I think it's not so far from the Spain statistics yesterday, the keynote, and we have a lot of mileage, and we can then count the number of accidents with personal injuries or fatalities, and then you can calculate the average distance between two accidents of a given category. Perhaps just all accidents, it's about 340,000, and on autobahns, nearly 2 million. Looking for personal injury, it increases by order of magnitude in both cases. And if you look for fatalities, you have 200 million or 660 million kilometers between two fatalities. And this big number is on one side very good because it shows that there's a high level of safety. But on the other hand, this is a risk reference. Not to have more accidents in categories of personal injuries and fatalities with this number. How can we come to a way to do this? And just to make it more clear, to compare to lifetimes of human. If one person have about 55 years license and practice driving with approximately 14,000 kilometers per year, which is average for Germany, we have a lifetime mileage of 770,000 kilometers and about 15,000 hours for driving this. So, if you look for this number, the lowest number, the registered accidents of 340 kilometers each, and a self-causation rate of about 60%, and the same for the average of fatalities, you can count that you have an average in life 1.4 accidents caused by you. So we have always to see all the situations you have in one life, in your experience, have to be a kind of reference for an autonomous driving vehicle. But if you look for the fatality rate, it should take 450 lifetimes of experience that there shouldn't be any accident with fatalities by an autonomous system. So the conclusion first is, we know the driver makes a lot of mistakes, but only few of them leads to a consequence with injuries or fatalities. And that's a good way, but it's not easy to look for machines to do it in the same way. Conventional ADAS the advanced driver assistance systems, will be tested with different tools, but the major part is to have a kind of endurance driver test. The word is not always clear. It means also customer close behavior driving systems. Then you have to see what occurs on 1 to 10 billion, what is now about state of the art. But the main point is, today ADAS, we have the driver, and so the design is more for controllability, not for safety of the system in all situations. The driver will supervise. So then we can see what should be, if you take the same strategy, what have we to take for travel distances for autonomous driving. We can make some kind of statistics. I think it's not bad to start with a Poisson distribution, because an accident with this low rate is similar to the independently occurrence of this. And let us assume we have a value where 2 events or accidents will occur with the driver, and we say the autonomous will be twice better. And then you can look how often you will get in this distance 0 events, 1, 2, or 3, or 4 events. And if you look for 0, 1, or 2, it is not really, you cannot differentiate between them. There is a higher probability if you have 0 that it is for the first time, for the first case, but it could also occur for the given probability for the second case. So you need a higher number of expected values to differentiate the expected values from one group to the other one. For that you can compute a distance factor. That means how bigger must be the mileage compared to the reference mileage. And if you just the luck that there is no event, it should be 3 times more. If you have about 4 or 5, it should be nearly 10 times more. Then you can differentiate on a level of 95% confidence or an error level of 5%. But if you have a system which is similar, same expected value, then you will not reach with a high probability this stage. Because it's also like the error probability, the occurrence will be about 5%. If you will look a reasonable figure with 50% success, then you need another factor, the performance factor. You have to be better in order to reach this distance factor. The best distance factor is 3, and you need a system which has to be more than factor 4 better than the reference level in order to have this with 50% chance. If you have just twice better, you have to take about 10 times more. So all the figures given in the statistics on mileage per accident, you have to factorize with this distance factor, and I think it is realistic to have about a factor of 10. Oh, this is for the animation. And if you look for this, the lowest figure is about 100 million kilometers, but you can also generate figures with fatalities on perhaps autobahns or motorways to come to 10 billion kilometers. For that reason, you say Google did a lot of work, great work, but they are just marginal compared to this level of needed mileage. But then you can discuss with some other engineers for safety certification, and they always told, no, we didn't such thinking for the conventional system, like today vehicle systems, ESP and so on, and we don't do this for the aircraft. If you will make the same figures for aircraft, you come to trillions and so on. So there's must be a fundamental difference if this is true. And let's check. There is a basic difference. We have a very good knowledge on this green part of the vehicle. We know all how a failure may occur, all the different reasons for this. Perhaps by corrosion or temperature change or load. And for this we have always tests to estimate the effect on the lifetime. And we have very good processes now for electronics with the ISO 26262. But we do not have any strategy how to certify safety of an intelligent system. With the basic the models of Rasmussen and Donges to just give them only blocks for beating, but there's no really a model behind to predict something and to certify safety. So that's the reason we have a very big lack of information. And if you look on an approval, you will see that you can develop a lot, but then you come to the point where you have to stop. That's the approval trap. And then we can perhaps analyze what is missing in order to bridge the trap. If we will not stop the direction of autonomous vehicle, and I think nobody here in this auditorium will do this. So we have a lot of question marks. We do not know currently worst case test cases. We do not have metrics for identification of criticality of situations. The environmental influence on perception is not always clear. And how can we test behavior to be a high robustness and safety? And if we use simulation methods, which is typical with model in the loop, software in the loop, hardware or vehicle in the loop, yes, we need it, that's obvious, but how can we say that this is valid? And up to now there's no idea to validate. And then we have to look for our methodology. Do we have the representative cases? What is necessary for an approval purpose? All these question marks has to be responded and to be clarified. And the question is, how can we come to this situation to gain the missing knowledge? One important point will be the evolution, so all the things in between. Two ways of evolution, in my point of view, you can see. One is that what it was expected 5 years ago, when you always look just on the roadmaps of the car manufacturers, they will make a functional evolution. You have predecessor functions, and with the predecessor functions you get a lot of databases, information about situations, specific road parts of problems, and you can collect sensor raw signals. You can establish for that test cases, for real and for virtual tests. You can do this on a virtual assessment of automation in field operation in such a way that you have in mind, it means processed but not with an actuator, and the new function, and then can assess if the behavior is okay. And you can make the simulation more and more realistic, and you also can collect statistical data for risk assessment. This will be always very helpful to generators. So then we have just to look what is the evolution path. But if you look for the possibility of autonomous driving, you will find not one. You can generate thousand types of autonomous driving. So it was not clear from which side we will come. And one way is the evolution triangle to start from 3 corners. One corner is always in mind, then we come from simple scenarios, car following, just lane keeping, perhaps a little bit lane changing, and make this more and more going to the highway pilot. Of course, you start with a simple scenario. Another simple point is the low speed, because the low speed has advantage. There's always a simple fail-safe state. Just stop. And then we can make an evolution coming from the speed, from parking to valet parking, and combine something in congestion assistance. And the first one was full speed range ACC. And the third one is coming from the high risk. High risk in that case has a big advantage that it's easier for a machine to decide this situation is more dangerous without an interaction as with an action. And this is being done with collision mitigation brake, collision avoidance brake, perhaps collision avoidance evasion, and coming to the last one, an emergency assist. If there is a heart attack of the driver, that the car will drive to a fail-safe state. And this is also a very big part for the general evolution, because if you can do this, then you have also the fail-safe state for the scenario at the top. So for this you will find like a color triangle that you need for white as well, red, blue, and green. And today we are really here, and then we have to come closer to the center. But it makes clear it's not so easy to find a predecessor-successor system. Another way is what I called here use case extension. So we will not make gradually stepwise automation. We will start with full automation, but just for a limited area. Just few roads and more roads. And there's a big advantage to start with this. We do not have statistical data which we can compare. So it must be just safe for this first part of the use case. And later we get more and more field experience and makes the system more and more mature. And this can be always combined with a supervision system by a provider and could be controlled in case of safety problems on given parts that they will shut down their function. The Google approach, especially with a small car, is similar to that way. If you make a comparison between, you will see the difference. Here we have the full operation area, but not full functionality. Then you have the full functionality, but the operation area is first limited. And you do not have such an approval trap, because you have to just approve on an absolute value of safety or an own criteria. It's not a criteria of 100 millions or billions of kilometers. For approval, you can say you will use some virtual techniques of simulation. Yes, you can do, and you can do a lot in between real driving and software in the loop. In general, there's a big potential, but you have always a problem of validity. The virtual approval could be part from the idea running the tests so that you come to similar travel distances in the computer. If you will do this in real time, you have to see, in principle, this is about 2,300 years. So if you will do this in 1 year, you need just 2,300 computers or systems can do this in real time. It is not cheap, but much cheaper than to do this with 1 billion kilometers. 1 billion test kilometer typically has to be factorized by 3 or 5 euros per each test kilometer. So you can see the invest of test kilometers and look for this one. Then you need just validated models, component models. You can check first the validity with component testing systems. Environment conditions you have to derive from test drives. And the vehicle dynamics is the lowest problem because you always can do this with test maneuvers as is state of the art. The situation creation is a little bit more critical task I will show later. You can do this by permutation principle or by stochastics like Monte Carlo approaches. Unsolved now is how to validate behavioral models of other traffic participants. That's a big point to see how can we all the behavior variants, which are also not from the subjects different, it's also intra-individual. Perhaps the behavior this morning after the event yesterday might be different to the behavior when we have a sleep with 8 hours. So we have to take into account, and we do not have clear figures about this. But situation generation is not easy. You will find a lot of sceneries, static circumstances, and you can make many constellations of traffic partners. So if you just look for the simple lane change maneuver to the left or the right, you have, in principle, to take 24 vehicles which could be relevant for a given situation. And they can have always different speeds and different behavior, decelerate, accelerate, change, and so on. So you come in a very high permutation problem. And it will overload any computer cluster you can imagine. It's very easy to calculate this. One problem is, for the evaluation, you first just start, it will occur a virtual accident and just counting them compared to the accident in real life. But that's a big problem. And there, the question, how can we come to another approach to avoid the permutation just counting virtual accidents? One way could be to decompose the task of automation. There's a scheme used from GRAB coming from analysis of accidents. And they could say, if there is an accident, at least at one layer of this, some mistake was done. So if we can generate safety on this layer with given criteria, we have the chance to avoid the full permutation problem, and we can make permutations more in one layer and combinations of this. This gives you hope that you first can modularize the tests. If the test and the architecture is compatible, then we have a very good chance to reduce and reuse the test results. And in general, we can always look for each layer, what is the worst case combination or worst case part, and there's no need to combine less critical parts of this for the given situation with the other layers. So you can find out the redundant test and can delete it from your test catalog. But you need new criteria for pass-fail on the decomposing layer. A matrix for this, which is now not available. If we can do this with a matrix, there is some hope to find a performance comparison between human and machine, and we don't have this always with the accident number. But it's an open promise. Don't know. In general, the virtual approval has a big chance, but we have to find if the test case catalog of this one will be representative. A minimum set is just to check the given reconstructed accidents, which should be always part of this. So you can take GIDAs or other technology to see if this is done. But it will not help too much because nobody knows about the different behavior perhaps of humans react on autonomous driving. Because autonomous driving will not a pure copy of human driving, because then we cannot get the safety level.
Hi there! We are recruiting volunteers for the ITS podcast. If you like our show and you think you can share some of your time with us, please let us know. Send us an email to ITSPodcast@gmail.com. ITSPodcast@gmail.com. We will appreciate it. Now let's get back to our today's interview. Thank you.
So, general simulation will be important, but it will not work in the beginning. That's the point. You need, for beginning, some other strategy. But you should always look to build up the capability to do this. So we have to find a little bit other words. Next point was to say worst case testing. Principal idea is if we have all the critical situations and we can see the system will handle these, so less critical situation will be handled too. If we have a clear criticality matrix, then we can really do this. But there's the same, we have a problem with matrix. Even only checking a critical situation, we have to look for a high variety. So it's not a short number of the worst case tests. Even in this, it is a big challenge. You can see, perhaps for time reason, I will come a little bit further with this. The driving test still is a very good basis in order to get real knowledge. But it will change the character. It's not more to say with 10 or 100 million kilometers there were very few accidents. No, the information is better to always collect the data from the real situations and to look, do we have this the same way in the computer for modeling and for test cases? Do we have the same behavior models on this? And we have also, is our test catalog always filled by the right test cases. We can make a priority on this test cases, by the worst case testing, and we have to look for a completeness. And only the real drives will help us to come to the validity and the completeness of test catalog. And if you make, again, statistics, you maybe make a carefully estimation if you look on the surprising events. Surprising means it was not stored in your database and it was relevant. Then you will find, first, you will find a lot you haven't more in your model library. But after some mileages, in thousands here, you will have less and you will have count just very few, and then you can make a trend line, and then you can extrapolate how many surprises you can expect it. And then to see that say you have a catalog quality of 99.9% completeness of test catalog and simulation models. So you can use it to make a quality identity. Then, if you put all things together, the matrix, stepwise evolution, and virtual approval, it should sufficient to bridge the approval trap. This was in former presentations one of the last slides, but after some thinking more about, we will have always some uncertainty if we do not have the validity for all the points. So we have a kind of chicken egg problem. We need data from the field in the market to have the validity for the alternative strategy. So we have perhaps the approval trap filled up with something, but will not really be sufficient. And so we have to look if there is an alternative way. And one is to say the introduction should be done risk limited. What does it mean? Let's first make a test drive. 1 million kilometers, 10 million kilometers. What is feasible? Then we get an expected value. We get a value about accidents of the different categories. And then we can calculate from this one a worst and a best case factor where the expected value should be framed in. Then you take the first case factor on the safe side. You can calculate the maximum expected risk for a given number of autonomous vehicles in the field. And if this risk, this worst case risk, is below a kind of a detection limit on the societal point and the statistical point, so that you will come to a kind of acceptance of this, then you can calculate how many cars you should introduce in a given phase. And then you can do this recursively using the travel distance from the new car in the field, again, a statistical basic in such a way that you can introduce new cars. We make some calculation on this. It's really on the limit. You will find cases and assumptions that it will not, it's a kind of exponentially grows, but exponentially grows in two ways. One way is in that way, hopefully. The other way is just going down and totally have a cumulative maximum number. I'm optimistic that the first can occur, but it is really at the limit. With such a strategy, we can for the first time come to a little bit different. We just skip the approval trap for the first time and then get the matrix. So we conclude. Currently, the approval trap is still existing. We have different promising approaches to overcome this trap, but the prerequisites for this are not state-of-the-art and really far from state-of-the-art to come to validity and completeness. Functional evolution or use case extension are strategies to get sufficient data, but there's always some doubts about the validation, and you have to see that the test drives will play for the first time the key role for the risk assessment and the methodological work for the alternatives. And the risk limitation risk introduction strategy might be a chance to tunnel the barrier or to skip the trap for the first systems. So that's the end of my presentation, and thank you for your attention.
You have time for a question? Okay, so let's go to that.
Very nice.
There's a microphone coming.
Thank you. Very nice presentation. Thank you. The question I have, as a human being, at least in America, you start getting to drive around 16 years old, and so you gain experience. So your first 5 years, you have a higher percentage of getting into accident than the last, let's say, 5 years. Or no, as you get older, you have probably higher chance. But anyway, so you don't have that uniform distribution on it. We think we understand the human driving behavior, given that we've been doing so much research for the last so many years. And we think that if every car on the road is autonomous, we don't have a problem at all. But if you take the human being as they get experience in driving and get the model for the autonomous vehicle that has experience already based on simulation and others, then now the problem is checking out where you have autonomous and human at the same time, driving on the same road. So how would the experience matter? Is it okay if we agree that we're going to have accidents, because we do every day, with autonomous vehicles, and we should not make a fuss about it? It's just we try to design it in a way that it can maybe limit the injuries or limit the fatalities and so on, but accept the fact there could be autonomous vehicle involved in an accident. So how do you see that?
There are two domains of thinking. If you think on the more philosophical way and looking more for societal reasons, it's hard to accept that automated vehicles will make accidents. But from a technical point of view, with this high number of situations, you cannot really fully avoid. You have some situations where a computer does this 10 times better than a human, but at one time it will occur. So in general, for society, it will be better if we have just the 1 compared to 10, but we have still to say there is a risk like other technical systems. And the expected value for all stakeholders should be better than the figure with human-driven cars.
Very well, this one is over. We hope you liked it. Please check out the ITSC 2015 YouTube channel in this podcast post at itsp.cicei.com to see the video recording of this keynote and all the others. We'll be back with more great ITS stuff. Stay tuned. This podcast is sponsored by the IEEE Intelligent Transportation Systems Society, website designed and managed by the Innovation Center for the Information Society at the University of Las Palmas de Gran Canaria in Spain. Soundtrack developed by Rubicon, language advisory by Manuel Arbela and Professor Son Williams from Clemson University, South Carolina. Audio edition, post-production and dissemination by the Institute of Cybernetics at the University of Las Palmas de Gran Canaria. I'm Javier Sanchez Medina from the IEEE ITS Society. We'll be back soon bringing you again the cutting edge of science at the Intelligent Transportation Systems podcast. Thanks for listening and drive safe.